Okay, time to get started. You may notice first, I'm on the wrong file. There we go. Okay, so we were almost done with talking about dot products last time. There's a couple of applications of dot products I want to talk through, and then we'll declare victory on that and move on to the next topic. So here's an interesting idea, geometric idea that's going to turn out relates to dot products in a kind of an unexpected way. So here's the idea. Let's suppose you have a vector v, right? And we want to compute something called the component in the direction of the vector w. So w is a vector like this. W defines a direction, right? And the idea is to say, well, w defines a direction. We're kind of interested in this v vector, but really, v is also kind of going off in other directions. I don't really care about all those other directions. I just want to know in the direction I care about, namely in the w direction, how far does v point in that direction? So for any football fans out there, American football, that is, the analogy would be if there is a play where the ball starts there and then the final tackle is made there, how many yards of gain are we actually talking about? And this distance here is not the gain in yardage, right? The gain in yardage is that distance right there, right? So anyway, that's the big idea. So how would we compute this? And it turns out it's really not that hard of a problem. It ends up being a little bit of trig, as it turns out. So the observation to make is that this component that I'm actually interested in, that's the component of the v vector in the w direction, that component relates to the magnitude of v by way of this little right triangle. And you can see in this right triangle, that angle theta, right? We've got a little trig relationship there. Cosine is purple over green, right? A little bit of high school trig. Okay, so that's the foot in the door. Everything else is just kind of algebraic trickery. The first little move I'm going to do is take this equation and a little bit of mathematical sleight of hand. I'm just going to multiply by 1 because after all, multiplying and dividing by the same thing is multiplying by 1, right? That's perfectly legal. So I hardly did anything there. And then I'm going to observe that what the numerator has turned into is exactly this old formula from last time for the dot product. Unexpected little appearance, right? Because of our little algebraic sidestep there. So, yeah, nice little formula. If you want to compute a component, you can do most of the heavy lifting. You can avoid the trig, right, by instead using the dot product. And we love this because dot product is three-function arithmetic. You multiply and add. There might be a minus sign in there somewhere. I mean, it's really trivial arithmetic, no trig needed. So, very cool, very nice fact. Now, obvious fact, if you're talking about in the direction of a unit vector, right, if instead of a random arbitrary vector, if you have a unit vector, well, the magnitude that you're dividing by, you're dividing by 1, effectively that denominator disappears, and you end up then with this little formula down here, which is very handy in a couple of ways, but I like to think of this as really kind of the natural way to compute a component, right? The formula just simplifies. I mean, if you go back up to the original picture and think about it, what is W's job in this original scenario? Its only job is to define a direction. Its magnitude never was supposed to matter, right? So why are we dealing with a vector that has an arbitrary magnitude? Let's take a vector that has a natural, most convenient magnitude. So if you define the direction with a unit vector, as would seem natural in the first place, components are computed with dot products. Another way you can say that is, and I just kind of like the highlighting thing, the act of computing a component in a certain direction is the act of dotting with a unit vector. Is everybody on board? All right. neat application. By the way, this is going to come up a lot. We're going to be doing quite a bit of this over the course of Math 212. Now here's another application, and this is actually going to be a surprisingly useful one as well. Foreshadowing for when we get into chapter 15 stuff in the future. So an old high school physics formula. And if you haven't had high school physics, no problem. Don't worry about it. Not going to assume it. There is this thing called work. You don't need to worry too much about the really nasty details of what work is. It's just think of it as the amount of effort. I mean, energy is the term, right? But it's the amount of effort that has to be expended to accomplish a certain task. And if you're talking about moving stuff against a force, then there's this easy and pretty intuitive formula here. Force times distance. The heavier the thing is that you're pushing or lifting or whatever the case may be, the more force you have to apply, the more effort it's going to take, right? I mean, stands to reason. Likewise, the further you're going to move it, well, the more effort it's going to take. I mean, it's just all kind of plausible. The problem with this formula is that there is this big if at the end. This formula only works if these two things, the force that you're applying. Quick pause. Let's think back to where we heard forces before. In this class, we heard forces as an example of what really should be thought of as a vector. Forces have directions, right? We're treating it as a scalar. That's intrinsically kind of wrong already. And then the displacement, again, that was our very first example of what should be thought of as a vector, not as a scalar. It's not just the distance. It's distance in what direction. Right? So these two directions have to be the same directions for this formula to be correct. If you change the direction, if the force is that way and the displacement's that way, this formula is wrong. It's just flat wrong. Right? Okay. So we're going to see if we can improve this. So here's the scenario I want to consider. Let's suppose we're moving like this. There's our displacement. We're going to, start here and there. And along the way, suppose that the force that I have to apply is in a different direction. The big idea is that the extent to which that force points perpendicular, who cares? Doesn't matter. Perpendicular, I mean, that's what happens when you're coasting on a bicycle on flat ground. The force is vertical. You're going horizontal. There's no effort required. You just coast, right? So perpendicular forces are irrelevant, which means that the only thing that actually matters is the component in the parallel direction. And that component, being as it is in the direction of the displacement, that is what you need to multiply by the distance in order to get the work. Does that seem plausible? Cool. So, hey, good news. We already have a formula for component, right? And by the way, the displacement's not a unit vector, so I do have to divide by the magnitude there. Displacement's arbitrary, right? And then let's think about the distance. The distance traveled is, well, kind of by definition, it's the magnitude of the displacement vector. That's a definition, part of the definition of a displacement vector. So we just multiply those together and notice that, very conveniently, check it out, these two things cancel and we end up with a very crisp formula for how to compute work from a vector point of view, right? Accounting for the possibility of things pointing in different directions is automated by the dot product, right? This is the thing that is doing all that sort of directional accounting for us. Is everybody on board? Beautifully encapsulates all the trig, right? So now let's look at another application. Again, a pretty straightforward application. Suppose this is your force and this is your displacement. If this were a high school class, then you'd have to think, oh golly, I'm going to have to draw a triangle and do some trig and figure out an angle, and oh my god, these vectors point in not only different directions, but inconveniently different directions, right? How are you going to compute the angle between these with high school geometry? Yeah, right? But with this formula right here, nothing to it. You plug them in, you dot them out. Dotting, again, is the world's easiest arithmetic, and nothing to it. Everybody happy? Nice application of dot product. Okay. This formula, by the way, is going to figure in very large in Chapter 15. Chapter 15 is, that's kind of what we're building up to throughout the entire course. That's where things get really weird, but also very, very beautiful. It's my favorite part of the course. Anyway, it's a lot to say about Chapter 15, but this is going to be a big player. Okay, the next topic, cross product and determinant. So this is where I'm going to have to pause on the math for just a quick second and talk about some course logistics. These notes that we're working from, that I've been using in Math212, I think I wrote them in 2015, fine, whatever. But multivariable calculus hasn't really changed very much in the last 10 years, so no problem, right? But nevertheless, I do have some even more recently written notes for Math219, which is not this course, right? It's a different course, different textbook, topics in a slightly different order, different assumptions of what students already have been exposed to, right? But it does remain that some of my Math219 notes are a little cleaner and a little more efficient, maybe. Pros and cons, but there will be some opportunities in this course where it'll be more convenient for me to use my Math219 notes than my Math212 notes. Now, when I do that in class, let it be clear, the Math212 notes are still sort of the index that we're going to use for keeping track of where we are in the course. Right. On the class schedule, it'll always will be references to page numbers in these notes, right? The Math212 notes. But that said, I will cover the material in the 212 notes sometimes by going through my 219 notes. So I hope that makes sense. And anyway, here we go, and talk about this thing called the cross product. There's a lot to say about this. By the way, there's a bazillion different choices that instructors can make talking about the cross product, because the cross product relates to this idea of an ordering of a list, which relates to the idea of a determinant. These are all different ideas, but they're all connected to each other and in very surprisingly strong ways. Geometrically powerful, algebraically succinct. It's so shocking how many relationships there are that we're going to talk about. So when there's so many different interconnected relationships, you can kind of go through that path in bazillions of different ways. There's a particular way that I like to do it that I think is most geometrically intuitive. And that's the one that I'm going to do. So it is going to be different from the order of the ideas that's presented in the book, different from our Math212 book, different from the Math219 textbook, which are different from each other. So anyway, it's just kind of a weird situation. But I like mine as being the most geometrically intuitive and satisfying. So here we go. I'm going to talk about the geometric aspect of an order of a list. So here we go. So first of all, what is a list? An ordered list, I should say, but whenever I say the word list, you should always interpret an ordered list, as most lists, right? The idea is it's kind of like a set of two vectors. I have here two vectors, but the distinguishing feature of it being ordered means that this is not just a set and you can write them down however you like. The one that's listed first is to be thought of as being first, and the one that is listed second is to be thought of as being second. So the list is in that order, A first, B second. Everybody see what I mean there? So here's the thing. A could be that vector, B could be that vector, in which case this list, where A is first and B is second, wouldn't you be tempted to call that counterclockwise? At least in this case right here, right? Okay, well, that's if A and B happen to be those two vectors. But if A and B instead were like so, A being that one and B being that one, well, A first, B second, wouldn't you be tempted to call that clockwise, not counterclockwise? So most, in some sense, most of the time, when you have a list of two vectors, it's going to be one or the other of these. It's either clockwise or counterclockwise. And there are exceptions now, of course. The exception would be, actually a couple of different exceptions. Either the vectors are pointing in the same direction, then it's neither clockwise nor counterclockwise. Ooh, what if one of the vectors was the zero vector? What if the other vector was a zero vector? What if they were both the zero? Oh my gosh, right? There's various different annoying little possibilities, all of which are linearly dependent. I don't know if y'all have seen that term. Yeah, if you haven't, don't worry about it. But linearly dependent in this context, we're going to take as basically meaning it's neither clockwise nor counterclockwise. And generically, it means that one of the vectors is either a multiple of the others or something along those lines. Cool? All right. Okay. Yeah.
Can they be pointed in opposite directions?
Well, yeah, that's right. That would also be linearly dependent. Yeah, if you had one this way and one that way, then again, you'd kind of struggle to. There's no distinguishing. There's clockwise and counterclockwise. Neither one makes any more sense than the other. So yeah, absolutely. Yep. All right. So, why are we interested in this? That's going to get revealed over the rest of today's lecture. But a couple of neat observations I'll make. If you have a list, and I'm just going to streamline things here, AB, and if the vectors AB are such that that list is counterclockwise, as figured, let's think about what happens when you reflect. Right? If you look at the mirror images by reflecting over some line in the plane. Well, the mirror images are going to be as I have drawn here, and notice that A prime to B prime is clockwise. It's just the picture, right? So not really that big of a surprise, but the point is that the act of reflecting through a line turns one order into the other. And this is a general fact, and you can persuade yourself, I think, pretty easily by thinking about an analogous picture that mirror images turns clockwise into counterclockwise as well. Yeah? All right. So that's that. When you make a definition, there's always this looming question of: have I defined something that's geometrically natural, or did I just make up something that's because I'm lazy? 4 times 7 ought to be 47, right? That's silly business, right? So I think right off the bat, this already there's something kind of natural about how this idea of clockwise, counterclockwise relates to mirror images in a very natural way. So a little inspiring. Trading the positions changes the order. Again, pretty straightforward observation. If A is first and B is second, let's suppose that's counterclockwise. Changing the order would mean B first, A second, and again, that's going to change from counterclockwise to clockwise, or vice versa. Again, I think pretty geometrically satisfying. Here's a neat one. Order is independent of rotations. If you have a counterclockwise list, right, and then if you rotate, so I'm gonna do, so our rotation here, that, what this R does, R is gonna rotate vectors, counterclockwise by some angle, some fixed angle. All vectors get rotated the same way. Well, pretty believable, I think, that the result of rotating a counterclockwise list still counterclockwise. Right? Of course, no one's ever looked at a clock and turned their head to the side and said, hey, it's going the other way now. Right? Of course not. Right? Okay, all pretty geometrically satisfying. Okay, so now that said, and a quick reference, these concepts, clockwise versus counterclockwise, y'all have been familiar with since you were kids, right? Since you were, probably knee high. One of the first things that little kids learn is which way is clockwise, right? So very familiar. Now we're going to move on to 3 dimensions. We'll be looking at a list of 3 vectors, ordered list of 3 vectors. A first, B second, C third, for example. 3 vectors. In 3 dimensions, and trying to ask a similar question. Can we come up with a 3-dimensional version of clockwise, counterclockwise? And this is going to be one that, most people walking around in everyday life don't really talk about very much, but ultimately is just as natural geometrically. And so here's the version that we're going to talk about. I'm going to start by defining what means to be a right-handed list. This is a little bit weird. It takes a couple of seconds. Bear with me. The idea is this: you have to use your right hand. You're going to point your index finger in the direction of the first vector A. See, I've got it kind of down and to the left there. Okay, so there, my index finger is in the direction of A. One of the rules here, by the way, your index finger needs to stay parallel to your palm. So no funny business like this, right? Index finger parallel to your palm. Okay, next, you have to point your middle finger in the direction of the second vector. So keep in mind, that one's first, this one's second. So now, if I were to have done this for my first, this hand gesture for my index finger pointing in the direction of the first vector, notice my middle finger, I can't point it in the direction of B. My hand's oriented the wrong way, but notice, I can keep my index finger pointing in the direction of A and twist around my finger, if you will. Effortless. It doesn't cost me anything, right? I've got a lot of flexibility in how I rotate around my index finger, right? So rotate however you have to so that you can point your middle finger in the direction of B. And by the way, again, no what I like to call hand yoga. So no fair doing funny business like that, or right? Just a middle finger doing what middle fingers want to do, right? Okay, so there you go. Index parallel to the palm in the direction of the first vector. Middle finger bending naturally to point in the direction of the second vector. Is everybody with me? Okay, so here's the thing then, before we get on to the third vector. These first 2 fingers, these first 2 vectors, they define a plane. Your thumb of your right hand, again, bending the way thumbs want to, again, nothing weird with your thumb, please. Your thumb points in the direction of one side of that plane. Now, in this case, it's pointing on what you might call the upper side of the plane. That won't always be. Right? It could have been like this. My thumb could have been pointing downward. Right? In this case, as I have it drawn here, though, thumb is on the upward side of the plane. If that third vector is on the same side of the plane as your thumb, then we call that then a right-handed list. That makes sense to everybody? Okay. All right, so that's a right-handed list. Now, it doesn't always work out. It's kind of a coin flip, right? I mean, your thumb and that third vector, half a chance they're going to be on the same side, half a chance they're not. I mean, generically. So, for example, let's think again very carefully now. If A is first, A is like that. Okay, so pointing my index in the direction of A. And now let's see the second vector, like this. Okay, so index in the direction of A. Wait a second, my hand's not oriented right. I'm going to, again, capitalize on the twist in such a way that I can now point my middle finger in the direction of the second vector. Notice my thumb now points on the underside. For this to be a right-handed list, I would need for C to be on the underside of the plane. It isn't, right? C here is on the upper side. That's just not how my right hand works, right? That third vector. So it's not a right-handed list, but it's totally a left-handed list. Yes?
Which plane is C supposed to match up with?
So, yeah, you're supposed to compare C versus your thumb with respect to the plane defined by the first two vectors. So, yeah, whatever the first two vectors are, they define a plane. And there's a sort of a one side of the plane, and there's the other side of that plane. Yeah, that's right. Everybody happy? Okay. So, not hard to persuade yourself geometrically that most lists, and I emphasize we're talking about ordered lists, most lists are either right or left-handed. Kind of like most of these lists are either clockwise or counterclockwise. And there are various, kind of anomalous, little annoying sorts of thing that can happen. What if one of them is a zero vector or something annoying like that, right? Something goes wrong. The weirdest one, I think, is like this, where all three vectors, let's see it this way, none of these three vectors is parallel to any of the others, but they're all parallel to the same two-dimensional plane. Right? This is kind of the weirdest of the various possibilities. Anything that's not right-handed or left-handed, we call, again, linearly dependent. You can just say dependent, that's fine. And every trio is one or the other of these three. Again, with various different versions of this. Okay. All right, so already it's kind of analogous to clockwise, counterclockwise. It's got a lot of the same properties. A right-hand ordering, right? If you do a mirror image, if you reflect through a mirror, through a plane in space, the images, those reflections, will be a left-hand ordering. Nice little convenient little demo here, right? Little hand gesture demonstration, proof by hand waving. Sometimes works. Yeah, yes.
Could you explain the notation, like the apostrophes on the left-handed ordering?
Oh yeah, the little primes here. The primes are supposed to indicate that these are the reflected vectors. These are the prime is what happens when you reflect through the plane. Yeah. Okay, so mirror images, just like clockwise, counterclockwise. Trading any two of the vectors changes the order. I think similarly believable. Now there's a little game to play there where you take your right hand and you kind of switch them, and then you realize you broke the rule, but then you notice that that's exactly the left-handed rule. So I think geometrically satisfying as well. Independent of rotations. There's another hand gesture, literally a hand wave, where I notice I can rotate. If I have a right-handed trio of vectors, no matter how I rotate, as long as I rotate them all in the same way, this continues to be my right hand, right? So pretty believable as well. So these first three properties, the exact same three features that we saw for clockwise, counterclockwise. So as such, right-handed and left-handed, you really can and should think of this as being a three-dimensional version of clockwise versus counterclockwise. Okay. All right, now there is a fourth property I'm going to talk about. There isn't really a two-dimensional version of this, distinct from one that we've already mentioned. But if you have a list of three, you can talk about doing what's called cycling. So cycling means that everything moves over by one. The third one goes to the second position. The second one goes to the first position. The first one goes back around and to the third position. So push it. It doesn't matter which way you go, but you push everything over. Something falls off on one side, you put it back on the other side. That will always preserve the order. Not at all obvious. The best version of hand-waving proof of this that I'm aware of would be like this right here. This is the hand gesture. Can everybody see that? Sorry for those watching on the recording. It just won't come through. But this little hand gesture here, I think, is pretty believable. Okay. So, now I'm going to need to talk about some theorems. Now again, these are Math219 notes. Math219 assumes that you've had Math218, which assumes that you know what determinants are. Y'all have presumably not had a linear algebra course. You may know what determinant is, you may not. So anyway, in recognition of that, though, I am going to come over here and back to the 212 notes and show you what determinant is. This is just a definition. There is, by the way, a lot to say about determinants. From a linear algebra point of view, it's got a lot to do with solving systems of equations and existence and uniqueness and stuff like that. And there's some geometric interpretations. They relate to linear transformations, which is a linear algebra thing. There's a lot that I'm not going to be able to tell you in this class. What you're going to need in this class is to know the formula. And if you have a 2x2 matrix, then the determinant is computed by this formula right here, AD minus BC. It's a weird little formula. A lot of people like to think of this as that you kind of go down the diagonal and multiply, and then you subtract, which you get when you go the other way, the off diagonal, and multiply, if you like it that way. For a 3x3 matrix, the formula is weirder, and it is what it is. It's mysterious, deep ideas, as it turns out. And it's really hard to motivate it in a context like this. But here's the formula. Strange though it is, we go across the top row. You'll see here we have the elements in that top row. As I go across the top row, I alternate plus, minus, plus. I know that's weird, right? Again, why the minus? Deep water, right? That's a linear algebra thing that we don't have time to go into, but it turns out it's actually very natural. So again, for the moment, we're just going to sort of take that as a given. And then for each term, let's suppose we're looking at this term right here. That's what you might call the A1 term. You look at the corresponding minor. So you cross out the row and column that entry is in. You look at the other little leftover matrix, and you take the 2x2 determinant, a la that existing formula, of that little, what we call a minor, sometimes called a submatrix. Very weird formula. If you ever take Math221 or Math218, you'll hear a lot better discussions, more thorough discussions of why determinant formula is what it is. Here we're just going to state it. All right. So with that said, here are a couple of theorems that you can do with determinant. I'm not going to be able to prove these theorems. The proof isn't ultimately all that hard, but it is kind of deep. The proof requires using some sophisticated ideas of linear algebra that, again, maybe some of y'all, but probably most of y'all have not seen before. So I'm just going to state these theorems. You don't need to know why they're true. You just need to know that they're true. All right, so here we go. Really shocking how this works out. But if you have a list, an ordered, let's see here, back to if you have an ordered list, AB, this is in 2 dimensions. Ordered list of 2 vectors in R2. That means that one of the vectors is first, the other vector is second. Okay. You can use that to make a matrix where the first vector becomes the first column and the second vector becomes the second column. So if you have a list, that makes a matrix. Okay, well, neat fact. If you have a matrix, that defines this thing called a linear wrong color. Linear transformation. Now, again, y'all don't need to know what a linear transformation is. It's for our purposes here, it's just a function. And what I mean by this function that gets defined by this matrix is this function is just the action of multiplication by that matrix. That's all it is. You could multiply by a matrix, and that turns one vector into another vector. That makes a function. Now, just thinking things through here a little bit, you may notice that if I were to multiply that matrix, in other words, if I were to apply this function to E1, what happens to E1? Well, E1, if I were to put it up there, it's just a 1 and a 0, and if you multiply that out, it gives you the first column, namely it gives you the vector A, as it turns out. All right, now that's a little bit of matrix vector multiplication. You can just crank that out yourself. Notice that, how about that? It's weird, it works. Gives you the first column. And then likewise, if you do a similar thing with the second standard basis vector, you will get the second column out. So, said differently then, now let's sort of recap. If you have a list that defines a matrix, which gives you a function, which is something that turns these vectors into those vectors, and which now I'm going to interpret as creating from the standard square. This creates a parallelogram. Is everybody on board? So all of this came out of a list. By the way, I haven't made a statement yet. I'm just building stuff. I'm setting up the sort of the context for the discussion. If you give me a list, I can make a matrix, I can make a function, and that therefore makes a parallelogram. So now, with all of that said, here's the theorem. The theorem says that the absolute value of the determinant of the matrix is equal to the area of that parallelogram. That's way not obvious. Don't look at the picture and try to, oh yeah, I totally see that. No, you don't. It's really not clear at all. It's shockingly convenient, but mysterious in why it works. Does that make sense to everybody? Okay. Yeah, very weird. One thing I want to point out, and by the way, mathematicians love it when the following happens, and that is that even though determinant is defined in a very algebraic way, right? Look at this definition we have for determinant. It's extremely algebraic. There's no geometry in this picture. It's just moving numbers around, right? An algebraic definition, and yet it relates to a quantity that is intrinsically geometric. This is an eyebrow raiser. It's like, what? How could that be? Wait a second. This algebraic object, and yet it relates mysteriously to a unavoidably naturally geometric object. That's weird. It's fascinating. Is everybody on board? Okay. All right. The next one to talk about is a little bit weird. So it turns out that the sign of the determinant, so by contrast with the absolute value is what you might call the magnitude of the determinant, right? But so the sign is just is it plus or is it minus? Ignore the magnitude. Just is it plus or is it minus? Is going to tell us critical information about the ordering of that original list, and whether that original list is clockwise or counterclockwise, and then there's another interpretation we'll get to in a second. So I'm going to zoom out here so I can fit this all on. As I have it drawn here, looking at the way I had it drawn here, and by the way, I had to draw something. I arbitrarily, I had to put a picture on the page, right? I arbitrarily drew this as being a counterclockwise list. Right, so this case that I happen to have drawn for no particular reason corresponds to the first possible case. If the determinant is positive, then your original list is counterclockwise. Is that cool? And now let's think about what that looks like geometrically. Counterclockwise, of course, looks like that. But don't forget these vectors A and B, they effectively came out of E1 and E2, and E1 and E2 are unavoidably counterclockwise. And so now let's think about geometrically, what does this look like? If you have a counterclockwise list and you transform the plane around in some way that counterclockwise remains counterclockwise, I'm going to say in some sense the plane kind of remained right side up. You couldn't have flipped it upside down. If you flip it upside down, counterclockwise becomes clockwise. So many things may have happened by this function. Things may have been stretched out or rotated or sheared, right? Various different possibilities, but there was no flipping because flipping unavoidably turns the order the opposite. Okay. Now, let's entertain another possibility, and I'm going to have to come up and edit my picture here. Another possibility is, and I'm gonna kind of cheat here and just kind of scratch out the labels. And let's suppose that now, let's suppose that was the A vector, and this is the B vector. Oops, I didn't do that very well at all. There we go. Now let's look at this list. AB there is clockwise as it's now drawn. Well, wait a second. It remains that A was the first vector. The first vector was the first column. The first column is the image of E1, which is the first standard basis vector. These vectors still relate to E1 and E2 in exactly the same. They're just different vectors. And so what's happened then is now this function called T is turning a counterclockwise list into a clockwise list. That means just from a geometric point of view, there has to have been some sort of a flip in that function. And if not a flip, you can think of it as a mirror image. It's sort of inverting through a line, or kind of a mirror image inside of the plane, sort of a deal. So that's the second case, and that second case corresponds to the determinant being negative. The vectors were clockwise, not counterclockwise, and thus there is an inverting of the plane. So these are, again, the two primary cases. The determinant is usually either positive or negative, one or the other. There is a third possibility. This, I suppose technically, what are the odds? But in real life, pretty good odds, side note, right? Anyway, if the determinant's exactly 0, turns out that corresponds to a dependent list. In other words, the list itself was neither clockwise nor counterclockwise. And I don't have time to go into the linear algebra on this, and we can ignore this part. But it's not a question of whether the plane does or doesn't have a reflection in it. It's that the entire plane is being squished into a line in some form or another. That's again, we don't really quite have the linear algebra for that. So 3 cases, but the big idea: this algebraically defined determinant strongly connected to these geometric interpretations of both the vectors and the resulting function. So algebraic to geometric connection. Again, mathematicians love it when that happens. Okay, weird theorem. Everybody on board? Powerful stuff. Not going to prove it. A little bit beyond what we can do in this course. But there's a 3-dimensional version of it. Again, I'm just going to kind of wave my hands at this. It's exactly analogous. If you have a list, that gives you a matrix, which gives you a function, which turns a list of standard basis vectors into a list of images, which again, easily checked, are just the original vectors. That's all the same setup, just 3 instead of 2. Okay. And again, we have these ridiculous connections between the algebra and the geometry. So the determinant of the matrix, the volume of this resulting parallelepiped, by the way, they call this a parallelepiped, closely connected. Absolute value of the determinant, the magnitude, in other words, of the determinant tells you the volume of the parallelepiped. Algebra to geometry, eyebrow raiser, all that. And again, totally analogously, the sign of the determinant. this algebraic aspect of this algebraically defined thing tells you this intrinsically geometric information about right-handed versus left-handed. That's all geometry, right? And whether there's a mirroring, inverting in the linear transformation or not, also very geometric. So totally analogous to the two-dimensional theorem. Is everybody happy with that? Again, no proof. Don't worry about it. You don't need to understand why. It's certainly not obvious. It's way not obvious. But this is true. Okay. All right. Yeah, shocking facts. So with that said, I'm going to dive into the actual main topic here, which is to talk about the cross product. It's really important, though, when you're doing cross product to have an understanding of determinant, how determinant relates to geometry, as we just discussed, and to have an understanding of this right-handed versus left-handed and clockwise, counterclockwise stuff as well. So I'm gonna define cross product kinda analogously to how I define dot product. I'm gonna write down a formula, seemingly out of thin air, and apologize for doing that, right? And then with owing you an explanation of why this is natural, I'm going to go through a bunch of properties of it and see how that in fact this behaves in really geometrically natural ways. So here it comes, the cross product, which we represent with this notation. Notice the little x kind of times. That's why we call it a cross product. Again, reminder, there's two different kinds of products. Dot product, cross product. They are totally different. You have to indicate which one. If you say product, I don't know what you mean. The context does not make it clear. You really have to say specifically, and your notation has to indicate specifically which multiplication you're doing, right? Dot or cross. So you can't just write AB. That doesn't work at all. The cross product is defined by this seemingly arbitrary formula. Pretty weird. What's with those minus signs? Right? Very weird looking formula. Now, in my life, I've used cross product a bazillion times and I have never memorized this formula. Ever. Not even once. Not even the very first time I learned it. Right? Because shortly after I was presented this formula, I was presented this alternate formula, you might say, called a symbolic determinant. A symbolic determinant just says, look, we have a formula for determinant. And yeah, I know determinant is supposed to be something you do to a matrix. And a matrix is supposed to have elements that are numbers. And I can see very clearly that there I have a seemingly element of a matrix that's very clearly not a number. That's a vector. You're not supposed to do that. This isn't really a matrix in some sense, right? So I'm taking a weird liberty here. I'm putting a square peg into a round hole. So we should be uncomfortable with that. And that's why I'm going to say symbolic determinant. So this is not a real determinant because the thing I'm applying it to is not a real matrix. Granted. That said, if you kind of ignore all that and just proceed anyway as if it makes sense and crank out the formula. Okay, we're going to take this thing and multiply by the determinant of this submatrix. Oh, check it out. You get exactly that first coordinate. And then if you take this thing here, and don't forget the minus sign when you get to the second one, right? And then you look at its submatrix, take that determinant. Oh, that's exactly that right there. And then just proceeding along, this one times it determinant of its submatrix gives you that right there. So how convenient is that this symbolic determinant will totally compute your cross products for you. You don't have to remember all the minuses and wait a minute, is the sub 2 times sub 3 minus sub 3 times sub, which way does it go? It's easy to get that all backwards and messed up. The existing formula for determinant does all the bookkeeping for you. This is the formula that I encourage you to memorize. Now, everybody's different. Everybody's different in terms of how they remember stuff and how your brain works. And, of course, do whatever works best for you. Again, in my life, I have never memorized this formula, but if you trust yourself, if you have a better memory than I do, which I bet most of you do, you might want to memorize both of these formulas. And I think that's fine. But you should definitely memorize this one. Yeah?
Can you just replace the basis vectors with ones?
No, because then for one thing, you'll get a scalar and not a vector. Right? So very importantly, when you're looking at this submatrix, you need that value to go exactly into the first position. And that's what having E1 here does for you. Yeah, no, I hear where you're coming from, but yeah, it's very important that those be standard basis vectors to get the right formulas into the right slots. Yeah, good question. Anybody else? All right. Cool. Okay. Oh, yeah.
Why is the second term negative?
Deep question, well beyond what we can talk about. That's arbitrary. That's just a weirdness of the determinant formula. That's just how determinants work. And, right. Now, great question, but I don't have an answer. There's no appropriate answer in this class. Yeah.
I forgot that.
Nah, no problem. It's all good. Okay, so here's a weird fact, and this is arguably a good motivation for where this wacky formula for cross product came up in the first place. One could speculate. Notice that if you take the cross product, and if you dot it with some other vector, and if you take the resulting expression and multiply it out, lo and behold, you get exactly a literal actual determinant. An actual determinant of a matrix with actual numerical entries. And it's just the algebra of it. You dot it out, check it out. It totally works. Just algebra. And you can even kind of see it happening. What's beautiful about this is the simplicity of it. That whatever is the first vector in this little expression, that first vector goes and becomes the first row. The second vector becomes the second row. The third vector becomes the third row. Could not be more convenient. What we call a triple product is actually a determinant of a closely related matrix. Now, the semantics, a little bit annoying, but you do have to be careful. A triple product is something you do to a trio of vectors, more specifically an ordered trio, an ordered list of vectors. You can't talk about a triple product of a matrix. That's not a thing. Right? Likewise, determinant is something you do to a matrix. You can't talk about a determinant of an ordered list of vectors. That's not a thing. Right? So, case could be made that triple product is just kind of a necessary linguistical, adaptation of determinant in the sense that, come on, if you've got a list of vectors, you can make a matrix. So, when you hear triple product in your mind, you should be thinking determinant. And you got to turn a list of vectors into a matrix. Is that cool? All right. So why is this formula important? Well, this is one of these beautiful little connections in math. We already have pretty impressive understanding of determinant. Powerful connection to geometry, volume, right hand, left hand, all of that jazz. We understand determinants very well. We also have a pretty good understanding of dot product. Right? So dot product and determinant we already understand. And this triple product formula relates that to cross product, which we're trying to understand. So having a formula in which you understand everything in that formula but the one little thing that then effectively you can kind of use your understanding of what I have in purple to gain an understanding of what I have in blue. That's the strategy. Okay, and that bears out. Now, sadly, we are now at the point in this lecture where I'm going to have to, just for realism, reasons, I'm going to have to actually do a little bit of skipping through some stuff. So everything that I'm about to skip, you are absolved of all responsibility, right? So you don't have to. I'm not going to leave you hanging on some deep ideas here, but we just don't have time in the course for me to talk through these proofs and how the proofs of these results come about. So you're absolved of these proofs, but you are responsible for these results. And that's what I'm just going to talk through. If you are curious as to why these theorems are true, I do encourage you to take a look at these proofs. They're right there. You have these notes in the, what's it called, course materials section of the website. This is, by the way, this is the file called Math219 Notes Chapter 1 or something like that. This is all the Math219's Chapter 1 notes. So it's right there on the web page. You're welcome to pull down this file and read these proofs. They are beautiful. They are geometrically elegant. They're a little bit mysterious. They're kind of deep, but they also take a little time. Yeah.
So the triple product returns a scalar. What does it mean geometrically? Would it be like the
One more time, say again.
The triple product returns a scalar. Right?
Yes.
What does it mean geometrically? Would it be
It means determinant. Triple product, you should, again, think of that as being basically kind of like a determinant, just where you, the relationship between the matrix and the list of vectors is that, vectors 1, 2, 3 become rows 1, 2, 3. Yeah.
like as volume then?
Well, kind of, but it's really not the same. I mean, the connection to volume, devil's in the details, right? It's the absolute value of the determinant that's the volume. So it's connected to volume, yeah, but it's also connected by the plus or minus to right hand versus left hand. So it's both. Yeah. Is that cool?
Yeah.
Yeah, yes.
Do we only have to, define crossproduct in R3?
Correct. That's right. Now, so we're accustomed to seeing operations like, plus and minus and times and stuff like that as what we call binary operations. In other words, two things in, one thing out, right? That's how plus works. You give me two numbers, the result is one number. So it's called a binary operation. So as a binary operation, cross product is peculiar to 3 dimensions only. Just 3 dimensions, right? Now, that said, I will acknowledge what would the term be, if there's more than 2 vectors that go in, if you're allowed to define a more general kind of product where several numbers go in and, or several things go in and only one thing comes out, then yes, you can define a something that's kind of like a cross product for any number of vectors. And it is a cool discussion, but it's mostly linear algebra. And so, yeah, we're not going to deal with that. And as far as this class is concerned, 3 dimensions only. Yeah. Yeah.
If you're trying to do a cross product of vectors in 2 dimensions, couldn't you just pretend they were, let's set the third coordinate to 0?
Kinda. Yeah. There's games that you can play, but yeah, that's going down a path that we don't need to. But yes, that is a clever idea, and that does allow you to do something of a sort. But yeah, it's not quite the same. Yeah. Okay. Cool. So, first fact. Very important fact to understand about cross product. The cross product is always orthogonal to both of the inputs, right? Whatever your first vector is, right, it's going to be orthogonal. The result will be orthogonal to that first vector. Whatever your second vector is, the result will be orthogonal to that second vector also. And you can just straight up compute the dot product of your cross product with that first vector and with that second vector, and you can just directly confirm that these are 0, and that is the definition of what orthogonal means in the first place, right? So pure algebra, but there's also a really slick geometry argument here that I encourage you to look through, and it'll leave you it'll feel like a magic trick in a way. Wait a second, how did all that come together? It's really kind of beautiful. But neat fact. Let me say this a little bit differently. If you have a pair of vectors as we will often in this class, have a pair of vectors, and I want to find something that's perpendicular to both of them. Take the cross product. Does exactly that. Okay. All right. Next fact. Wish I had time to talk about the proofs. Very beautiful. Triple products cycle. So, in other words, if you, let's see here, pencil mood. If you move the, let's see here, the third vector into the second position, the second vector into the first position, and the first vector into the third position. If you cycle a list of vectors, the triple product is unchanged. And I think that's a pretty mysterious fact at first glance, because a vector like, let's see here, a vector like B here that was originally part of the cross product over here is not part of the cross product. It feels like these ought to be totally different things, right? But they're not always the same. Yep.
I guess like my question is, does B cross product C equals C cross product?
Great question. Fantastic question. I'm going to get to that. For the moment, for dramatic purposes, let me leave that unanswered. But we will get to that question. But let me point out another great thing about that question. Remember that when you define a new operation at any point in any class, if you're doing, you make up new stuff, you can't assume that it's going to behave nicely, right? Very often, new stuff does not behave nicely. So good for you for not assuming, and I will come back and address that. Yeah. Okay, here's a weird one, and this is one of my favorite proofs. I wish we had time to talk through all of this. We just don't have the time. So again, I encourage you to take a look. But all I can do is tell you the result here, and that is the magnitude of the cross product, not the cross product itself. The magnitude of the cross product shockingly gives you the area of the parallelogram that you get by looking at those two vectors. So the parallelogram is this thing right here. The parallelogram defined by two vectors, like that. So the cross product, by way of its magnitude, tells you how to compute an area of a parallelogram in space. Very weird. If it were a parallelogram in the plane, we'd use determinant, but this is three-dimensional and everything's just different. Magnitude of the cross product is what does it. Is that cool? All right. By the way, do notice my notation here. My notation, the two parallel lines followed by a list of vectors means, use those vectors and make the corresponding parallelogram, or if there's three of them, you make the parallelepiped. You'll notice right here, this notation here, I've got the little parallel lines, and I've got three things that refers to the parallelepiped here. Well, there's a lot of edges. There we go. It's just notation. Okay. Neat fact. If a cross product is 0, the pair of vectors is linearly dependent. Another really cool fact. Surprising that this would work out, but it's kind of like, by the way, an old fact about dot product. You may recall from last time. If the dot product is 0, that means that the vectors are orthogonal. Right? So there's a different geometric interpretation if the cross product is 0. Okay. Here's a beautiful one, and another mysterious sort of seemingly hocus-pocus fact. This ordered list right here, any two vectors, followed by their cross product, where the first one first, second one second, that's very important. This exact list is never in left-hand order. Now, I write it as such just to be precise, but in practice, day in and day out, the way most people think about this result is that this list is always in right-hand order. Now, technically, it's not always right-hand order because one of the vectors could be 0, and it's annoying. But generically, that list is always in right-hand order. I just have to admit the possibility of zeros, that's all. Okay. And again, beautiful fact, again, I wish I had time, again, we don't. Here is an alternative way to think about the cross product then. And now I know I gave y'all an algebraic formula for the cross product. I pulled it out of thin air. But we've seen now various heavily geometric facts about it. And in fact, we've got so much geometric information about it, we have what I'm going to call a purely geometric characterization. You could take this as a definition, and some books do, not our book, the Math219 book, right? Not the Math212 book. Some books, though, start off page 1 of the section on cross products, and they define the cross product as follows. The cross product is the unique vector that's orthogonal to the inputs, whose magnitude is the area of the related parallelogram, and that makes this not in left-handed order. There will always be exactly one such vector. Notice that all 3 of these features, they're all geometric. This is a purely geometric characterization. And again, perfectly acceptable as an alternative definition for the cross product. So anyway, this is where I'm going to claim now that I feel like I've redeemed myself from having made up seemingly an arbitrary formula at the very beginning. I wrote down some arbitrary nonsense seemingly out of thin air. This is why we write down that arbitrary nonsense. It's because it behaves nicely geometrically. Everybody on board? All right. Okay. To your question about the ordering, it is not commutative. There is a minus sign there. If you switch the 2 vectors, you don't get the same thing. So cross product is not like regular scalar multiplication. And it's not like a dot product. Dot product's commutative. Cross product's not. A very rough proof of this, a hand waving, right, sort of intuitively satisfying proof. You might say first vector, second vector, cross product, right? We're going to always right-hand order. Well, if you trade the order of the first 2 vectors, first becomes second, second becomes first. Notice my thumb flips upside down. Right? And so this, ultimately, you got to set things up carefully, but ultimately this is kind of the point. This is why when you switch the order in a cross product, you get a minus sign. Is that believable? Okay. Cool. Yeah. All right. So yeah, you do have to be careful about that. Now to some underappreciated facts about cross product. I like to, and this is a kind of a linear algebra thing, but I do think that this is a nice point of view. If you think of cross product as a binary operation, it is what it is, and we've talked about that. Instead, if you think of cross product with a given fixed, unchanging, constant vector, say A, now it's not a binary operation anymore, right? This thing that I'm doing assumes one of the vectors. Now, what I'm doing this to is a single vector. So what I have here, cross product with A, I can think of as being effectively a function that you're applying to one single input vector X. So interpreting cross product as a function like this. This function has this lovely property called linearity, and if you haven't had a linear algebra course, you may or may not have, you probably have not seen this term linearity, but roughly speaking, what it means is that if you apply it to a linear combination, then the result is that same linear combination of the individual outputs. So in other words, you can do the linear combination either before you cross with A or after you cross with A. Makes no difference. Anyway, it's a nice property to have in mind. You'll see more in a linear algebra class about what this looks like. And then I also think it needs to get said along the lines of your question, not only is cross product not commutative, it's also not associative, right? Associativity would suggest that you can kind of move parentheses around however you like. Not so with cross products. Cross products are just not that nice. Like so much of elementary school arithmetic is everything works out nicely. Not so much with cross products. So heads up. Okay, a couple of applications. I'm going to be quick with these because this isn't a physics class, but I know that a lot of y'all are, not math majors. A lot of y'all are majoring in something that's about the real world in some form or another. So some real world examples, let's call it that. If you have an axis, maybe on a car, something like that, whatever, and if you've got a something sticking off of that axis that I'm going to axis that you maybe would call this vector R, and maybe it's like you've got a wrench. Maybe you're turning, trying to turn a bolt that's in something, or maybe maybe the green is the axis of a car, and you're trying to make the axle move. The engine's going to apply some force. But it's not acting directly on the axis, it's acting off of the axis that you have to get it to actually move. And at this point over here, suppose you apply a force like so, then if you want to compute how hard are you turning in some sense? How fast is the car going to accelerate? How tightly would you be able to turn a bolt? Or whatever, or untighten a bolt. Torque is the concept of how hard you're turning, how much of what you might call an angular force you're applying, and it's computed with a cross product. So anyway, that's a real world application. Here's another one about magnetic fields. By the way, magnetic fields, it's another physics thing. You don't need to really worry too much about that, but they are very important in understanding how electricity works and how electric motors work, which has always been important, but with the advent of electric cars becoming much more important, right? It's a really big deal how electric motors work. And one of the big ideas is magnetic fields, as it turns out. It's a huge essential part of how those things work. And here's the reality of how magnetic fields work. It's very strange, but if you have a magnetic field that's pointing in one direction, like this, and if you have a charged particle that's moving with a velocity, turns out, don't ask me why. Why did the universe get created the way it is? That's not a math question, that's a philosophy question, right? Or a religion question, right? Science is about understanding how the world works, not why it was created that way. Right? That's who knows. But the empirical reality is that when there is a moving charged particle in a magnetic field, that creates a force on that charged particle, and that force is computed by a cross product, as it turns out. Weird world that we live in. But that's what happens. All right, is everybody with me? Okay. So, all right, now we do have a couple minutes. We have a minute 20 left. I want to get through one little quick idea in the next section, which it happens to also be the next section in these notes. But it's just about how do we make the equation for a plane in space. And again, you may or may not have seen this previously. It turns out to be shockingly simple. And that is that if you define a plane, you can define a plane in a lot of ways, right? But if you define the plane by telling me a point that it goes through and a vector called n that it's perpendicular to, first of all, let's recognize there is exactly one plane that contains that point x naught and is perpendicular to that vector n, right? In some sense, n kind of, that tells you pretty much how the plane is oriented. And then having to go through a particular point nails it down, right? There is only one such plane. Easy observation to make that if you have a point, another point that's in the plane, I'm going to hand wave to the geometry here. The difference, come on, stylus, the difference, x minus x naught, has to be parallel to the plane because x and x naught are both in the plane. So that's parallel, which means that it's perpendicular. Let's see here. This parallel to the plane and that perpendicular to the plane must be orthogonal to each other. And then you just happen to notice that, having made that little quick, clever observation, this is literally an equation. And I'm going to move things around a little bit. It's a little bit prettier if you write it like that. And then you can give names to the coordinates and let the normal vector, for example, have coordinates A, B, C, and let your x that you're testing, let's let that have coordinates x, y, z. That equation that we just derived takes a familiar form, ax plus by plus cz equals d. So there you go. There's the equation of a plane. What I think is beautiful about this is that even though this kind of just seems sort of generic and kind of like, well, I don't know, it could be anything of this sort, there's meaning in that equation. When you write down such an equation, the coefficients that seem kind of arbitrary there, those coefficients are not arbitrary. That's secretly telling you what your in vector is. The vector that's perpendicular to the plane that kind of defined the plane in the first place. Right there, looking at you, right, encoded into the equation. And we're out of time, so I'll draw the line right there. Sorry to go over again. I really thought I could make it on that one. Anyway, calling it a day. See you tomorrow. Okay, see you.